Hello and welcome to our final topic, topic 12, analysis of algorithms. Most of the next two slide decks are going to be like very theoretical, and a lot of it is sort of just an introduction to this topic. You're going to see a lot more of this topic in future courses, should you continue with your computer science education journey. But we will do a little bit of an introduction here, and hopefully it will just kind of give you a little bit of a taste of what are some of the things we consider when we are designing algorithms or making choices for data structures, depending on, what sort of behaviors we might want to, what sort of tasks we might want to accomplish, I suppose. Okay, so we have a couple of learning goals here. We're going to learn a little bit about why computer scientists care about the major steps in an algorithm over the measurements that are like CPU time and more like hardware, things like that. We're going to talk about expressing complexity of some algorithms using what is called big O notation, which I've used the term before in these videos, but we didn't really talk too much about it. We're going to get a little bit more into its actual mathematical definition right now. We're going to compare and contrast running times of binary search and linear search using that term big O notation and break it down a little bit more than we have thus far. And we're going to do that also with insertion sort, selection sort, merge sort, and we'll discuss this idea of quicksort again and talk about its big O notation as well. So we're going to start off by talking about these searching algorithms and how we're going to sort of analyze them. So previously we'd seen two different searching algorithms. We've seen the linear search, which is just going straight through the list, element by element, looking for a target value. And then we also did the binary search, which required a sorted array, or a sorted data set, I should say, so that we could sort of use the knowledge of it being in sorted order to have our data set over and over again until we either find or do not find the element in the only possible spot it could be in within a data set. So we know that these two different algorithms have different performances, right? They have different speeds. And we've talked about that before. We've talked about how linear search, in the worst case would find the element in the very last element it checks. So it could have to do n checks if there's n elements, whereas the binary search only ever has to do log n checks, since it can cut out half of the data set every single iteration. So now that we kind of have that basis, we're going to talk more about how we can compare them. One of the things we can do is we can actually implement them and time them. But that is very dependent on things like who implements it, so how they choose to do it, how their level of understanding of efficiency in those algorithms, potentially the computer system we're using, if it's a new computer, if it's an old computer, if it has enough memory for certain things. It depends on the test data, right? It depends on how big of a test data size we actually use, because on a very small data set, the difference is pretty negligible, and we don't really see the difference that actually exists in these algorithms. So instead, what we do is we analyze these algorithms, and that's like a whole field of research and a whole topic in computer science. So the first thing that we can do, and we've seen this table before, is we can compare their relative speed as a way to sort of start to understand how to analyze these algorithms. So very quickly, we do see the difference between these two algorithms being quite large. Because when we double the list size, the linear search will then potentially double in the number of iterations of the for loop, and the binary search only adds one iteration. And if we look at 1 billion elements, we'll see that worst case, that linear search is going to take 1 billion iterations. We start at the front, we find it at the back. And in the binary iterations for the binary search, it actually roughly is about 30 iterations maximum. So we really start to see the difference in an n algorithm versus an log n algorithm when we start to increase our element size, our problem space. So when we want to actually analyze the speed of an algorithm, what we are talking about effectively is counting the number of steps or operations that are needed. And we try to look at it as a function of the size of the problem. When I say the size of the problem, I do mean relative to n being the number of elements or the inputted value or whatever it might be. So that's n is the size of our problem. So we can look at it in a couple different ways. We can talk about either as the average number of steps or the maximum number of steps. And the understanding these differences is really important. The average number of steps tells us, like, in most situations, on average, if you run it enough times, what are you going to, end up around? If you think about flipping a coin, like the statistical probability of getting a head or a tail, on average, it's about half for each. So maybe you don't see half when you only do one coin flip. Maybe you don't see half when you do 10 coin flips. But if you do 200 coin flips, 2,000 coin flips, 2 million coin flips, we start to see on average 50% of the flips are head and 50% of the flips are tails. So that is the average situation for coin flips. Now, if we consider the maximum number of steps, this is different. We're going to say, well, what's the maximum number of what's like the worst possible scenario? And if we think about it like coin flips also, since each flip is independent of the previous flip, it's entirely possible, not likely, but possible that you get all heads and 0 tails, or all tails and 0 heads, right? So that's like the maximum situation, is that we could go for a really, really, really long time and actually never see a head. In theory, right? Theoretically, that is the maximum. So that's the difference here. We're talking about what is the average situation versus the maximum worst case situation. In a list of 10 billion elements and a linear search, what's the worst case situation? What's the maximum number of steps? Well, the maximum number of steps is going to be 10 billion iterations of that for loop, because we find it right at the end. So for any kind of search, the size of our problem is exactly equal to the size of our input, right? It's going to be that n value. So we can really frame these analyses in terms of n, because it just depends on what n is. If n is 10, then worst case, we're going to have 10 iterations on a linear search. And if 10 is 10 billion, worst case, we're going to have 10 billion iterations of a linear search. So let's actually frame that now in terms of like some mathematical properties. So let's talk about linear search first, and then we'll do the binary search after. So the average number of times that that for loop gets executed is about n over 2, right? And we're not going to do all the math around why that's true, but we can understand why that would be true. If we think about a list of whatever size it might be, and we're talking about the average, sometimes we'll find it at the front, sometimes we'll find it at the back, sometimes we find it in the middle or somewhere in the middle, and we end up with this really nice Gaussian distribution, this really nice normal distribution, a hill right over that n over 2. And we're talking about average. So if we do a linear search on a data set a bazillion times, we'll end up with, on average, n over 2 loops to complete the linear search. However, of course, we do have the maximum that we have to consider, and the maximum is that n, where every single time we find it, we'd find it right at the end. And that's the worst scenario, is that we go all the way through our whole list, we either don't find it or we find it in the last element. So we end up with this average of n over 2 with a maximum of n times. Now, the number of operations that we need for each iteration is negligible. We don't care in these analyses. So when I say the number of operations needed, I'm talking about like the lines of code within a for loop. Because basically the for loop, the number of times the for loop runs is directly correlated to n, right? We say for in I equals 0, I less than n, I plus plus. We're directly correlated to n. Now, whatever happens inside that for loop is just some random constant value. It's just going to be 4 if statements, or 3 lines of swapping elements, or an if statement and swapping elements. Anything that's happening inside that for loop is the same for every single element in a data sequence. It's the same for every single iteration. So we just call it C. It's just some constant amount that occurs every single time for n. So then when we want to figure out what the average number of operations is going to be, we can then say C times n over 2. Because on average, we're going to have n over 2 iterations of our loop. And for each of those iterations, we do some C constant number of operations. And the maximum is going to be C times n, right? Because worst case, we run the loop n times. For each one of those times, we do C operations. We get C times n in the maximum number of operations in the maximum time. So T of n is the total average number of operations, so the total time that it will take to complete a given algorithm over n elements. So we're using that T over n to express the, like this is the function that we can use to determine the total average number of operations for an algorithm over n elements. And so for T of n over n elements in a linear search, it's C times n over 2. Okay. On a binary search scale, it looks a little bit different. The part where we say, you know, each iteration has some small constant amount of time, that's the same, because inside that while loop or for loop, however you write it, we're going to just be doing our if statement checks, moving our high and low and midpoints, like all of that is just some constant amount of work. So we still just say, okay, that's C. However, every iteration, because it is a while loop in this case, not a for loop, typically anyway, is cutting our problem space in half. We're always going to the midpoint, checking that midpoint, and then moving our bounds, our high or low bounds appropriately. We're cutting it in half, and then we cut it in half of that, which is a quarter of the original n. And then we cut it in half of that, which is an eighth of the original n. And then we cut that in half, and it's a 16th of the original n. And this process of cutting the data set in half over and over again is a log is a log-based analysis here. So the maximum number of iterations becomes related to the maximum number of times that you can cut n in half. And when you talk about cutting n in half and in half and in half and in half like that, we're ending up with a log base 2 of n algorithm. And typically we take the ceiling of that because we're going to be talking about the maximum number of iterations. So if we end up with something that's like 3.6 or 3.5 or whatever, no matter what we round up, because we'll just say 4, you can't do half of an iteration. And we're talking about the maximum number. So yeah. So for n of 15, for example, first we would search all 15 elements and cut it in the middle. Then we'd end up with like 7 or 8 elements, depending on what side we ended up on. We cut it in the middle. 3 or 4 elements, cut it in the middle. 1 or 2 elements, cut in the middle, we'd be done. So on average, the ceiling of log base 215 is about 3.9 and some change. So basically we end up with a maximum of 4 iterations for log n, whereas if this was a linear search, for n equals 15, we would end up with a maximum of 15 iterations. So that's how that initial table over here was formed. We took that list size value and basically we did n iterations. So linear was 10, 20, 20, 1,000, 1,000. And then for the binary iterations, we took the ceiling of log base 2 of that list size. And that's how those numbers were formed. And we can sort of now see how those formulas, those formulas for analyzing the speed came to be. We can see that here. So when we want to now talk about this in terms of T of n, the average number of operations is going to actually be exactly one less than that value. And there's some math that we could do to prove that that's the case. But for right now, you're just going to take my word for it, that the average time for T of n is some constant time log base 2 of n minus 1. So we just add that minus 1 to it. And again, for right now, you're just going to take my word for why that's the case. Now, when we talk about the maximum amount of time, since we already over here are taking that ceiling, it truly is just C times log base 2 of n. And again, remember that C is just basically everything that's happening in the for loop. Now, one of the things I just did was list some information about like what that C could represent. And I said if statements and like swapping out elements and things like that. And I hope some of you are sitting behind your screens right now and you're asking yourself, but what about another for loop inside there? Does that count as constant time? And the answer is no, it's not. So a for loop inside of another for loop adds to the complexity of this algorithm in a way that is indeed relative to n. So we can't just consider it to be part of C. So when we look at our sorts in a second, we're going to be able to sort of expand on this idea and see that. So when we compare these two algorithms, just before we get there, we can say that linear search approximately was n, and binary search is approximately log base 2 of n. The constants don't really matter when we're talking about, in a second, big O notation. We just sort of ignore them. And we also ignore things like the half there, right? Or a -1. A -1 is a constant. The half, like n over 2, is basically like saying 1 over 2 times n. So we can ignore that 1 over 2. We ignore the c constants. We're ignoring all those pieces because they don't really matter. They're the same across the board. And in kind of general, like loose, wavy terms, it's just because all we really care about is how the problem space is changing in terms like this, how the time is changing in terms of the problem space, in terms of that number of elements, that n value. So we can sort of just ignore the fact that there are some constant things that happen with every iteration. We just ignore them. Right, so the really important thing about these algorithms is to consider, as n grows, how does the number of operations actually grow? This is determined only by n. It's only, that's the most important factor here, is for us to consider how n is going to affect the number of operations. That c stays constant for every single element, so it doesn't really matter. It's always going to be there. But if n doubles in size, how does that actually affect the rate, like the speed of this algorithm that we might be considering? So when we talk about our big O notation, I'm going to give you a little bit more of a firm definition in a second, but that's exactly what our big O notation is. Big O is saying what is like the worst case scenario here of running this, and more directly, how does n affect the algorithm? So linear search is a big O of n algorithm, and we saw why just a moment ago. And I said we drop the constants and everything like that. We just leave the terms that exist in terms of n. So it's a big O of n, which basically is us saying, how will this algorithm grow as n changes? And this one grows at the same rate of n. If n doubles, the time will double. Now with binary search is big O of log base 2 of n. When it comes to what we're doing in computer science, I don't have the base 2 there anymore, but we can always make this assumption we're talking about base 2 unless otherwise stated. And now this one is saying if n doubles, in this, when we're using a binary search, the time actually only goes up by a small increment, right? It only goes up by log n, whereas the other one, the time was going up by like twice as much when we doubled it. So log base, or sorry, big O of n is basically saying that as n grows, the algorithm's time will grow at the same rate. But big O of log n is saying that if the n algorithm grows, as n grows in that algorithm, we're going to see the time only grow at a speed of log n. So if you can sort of imagine what those two different graphs look like, one is going to be straight up a diagonal because as n is getting bigger, the time is growing at the exact same rate. But in the other graph of an like log base 2 of n scenario, as n is growing, log base 2, it actually sort of tapers off a little bit, and we end up with more of like a plateau than a direct straight line diagonally. These are really easy to graph by hand or like by code or just looking online if you want to see what an n graph looks like and a O log n graph looks like. But that's starting to get a little bit technical, and that's something that we're going to actually see next course. Oops. Okay. So now I've said this word big O a few times, and I promised you a better definition of it. So the big O notation means the order of the function. It doesn't really mean like worst case, best case, average case, time, number of steps. We use all these words, but the O actually stands for the word order. So it's the order of the function. Just like we had like a T of n, here we're talking about an O of n, T of n being the timing of the function, O of n is going to be the order of the function. Basically, it means how the function grows with respect to n, and apparently it's also called Landau's symbol. I've never heard anybody use this term, but I guess whoever coined it, Landau, named it after themselves. So basically, when n gets bigger, what happens to our running time? What happens to our algorithm? what can we expect? And it's often referred to as the worst case complexity just because it is going to be, pardon me, as n gets bigger, what's the worst that can happen in terms of our algorithm? What can we expect to occur? As the needs of our algorithm increase, as the problem space gets bigger, how will the performance of this algorithm hold up? That's what our order of the function actually means. Okay, so when we're talking about this, we can say, let's let n be the size of the input. This isn't new for us. And we let t of n, capital T of n, be the function that defines the number of operations or the amount of space that's required by the algorithm on the input of n. Please notice the difference here that we're no longer saying lowercase t, meaning like the time that it was taking. Now we're talking about capital T, and capital T is a little bit more arbitrary in this respect. We're talking about defining the number of operations. So we're talking about defining the amount or potentially the amount of space. So it could be a time complexity, it could be a space complexity, and there are a few other things that often get talked about with respect to computer science and analyzing algorithms. How much space it takes up, how long it's going to be, those are those other two. So if this is the case, if those are the two definitions, n being the size of the input and T of n being the function that defines the number of operations that are going to be required for that input of n, then we can say that T of n is going to be equal to big O of f of n for positive constant c and then some value n naught, so some initial value there. So basically what we're saying is that the function that defines the number of operations, that T of n, can be equal to the order of the function for that algorithm. So we know for sure that T of n is going to be less than or equal to c times f of n. Right now, we know that to be true because we remove the c from everywhere. Think about that for a second. When we were doing the linear search and binary search analysis, we stripped away that c and that -1 and that over 2. We stripped away all these constant values and just left ourselves with f of n, with what it was in terms of n. But what that means then is that when we take that f of n and we stuck it into that big O, that order of the function, we're definitely sure that T of n, whatever we say T of n is going to be less than or equal to C times f of n, right? C times f of n can only be bigger because T of n is effectively f of n. And so we end up with this C being greater. Okay, and basically this will hold true whenever n is greater than or equal to n naught, meaning if we pick a base value for n, that value of n or anything bigger, this will hold true for. We can't guarantee it will hold true for smaller values of n, because maybe smaller values of n will end up with somehow a smaller analysis. But for at least this value of n and everything bigger, we can say, okay, yes, this is going to hold true. Okay, here are my graphs that I was talking about a little bit before. Oh, well, these ones aren't the log n ones. These are different ones, but still. Basically, I wanted to put this in a graph notation here because I know how hard mathy terms can be to understand and to look at. So in English, when we say that an algorithm is big O of f of n, so it's big O of some function of n, what we're saying is that there's some constant c and a starting value of n, so n naught or n sub O, typically referred to as n naught, such that all larger inputs of n will not be bigger than c times the f of n function. So this graph is exactly what I just said. If we look at the red line is like the real algorithm running time. And I'm putting real in quotes. You can't see me, but that's what I'm doing because it's not really quite all the way real. We're not like specifying the divided by 2 or the -1 or whatever. We're just basically saying that some operation of some constants on f of n will effectively graph to something like this. And then our blue line is what we're actually saying is our T of n. Our blue line is what we're actually setting our big O to. And you can see where I'm showing that n of 0. And the point here being that after that n naught, it is going to be guaranteed, we can mathematically prove that that red line will always be above that blue line. Before n naught, we can't guarantee that. That's not what we're saying about our algorithm. So we're going to set an n naught value, and we can say everything that is greater than that number of n. So as our problem space gets bigger, we can guarantee that our blue line here, our t of n, our running time, is going to be under that c times f of n. That's what we're saying. We're saying that the very worst case is that f of n, and we can guarantee that for any value greater as n grows, as n gets bigger. So this like n greater than or equal to n naught can sometimes be confusing, but if we just remember that literally what that means in English is as n grows, which we've said lots of times already. I can't say anything about as n shrinks. I'm saying as the problem space gets bigger, I can guarantee my running time will not be any worse than this given point. Right, so the goal is to find a function of n that's basically our upper bound. So that red line is our upper bound on the number of operations that our algorithm is going to need. That way we can say that the number of operations required by our algorithm is going to be big O of f of n. We're saying worst case, that upper bound, this is the most number of operations that our algorithm is going to require. Now, if you take 2140 in your degree, if you're continuing in computer science or just have a general interest in it, some of this ends up in 2140, where we talk about a lot more about data structures and how the data structure can affect this as well. So not just the algorithm itself, but also how a data structure could affect it. For example, quick little like side note here, we already know that we can only perform a linear search on a linked list. We can't do a binary search. But is there a difference between a linear search and how it's being conducted in a linked list versus an array, versus there are other options as well, where you might do a linear search, like a hash map or whatever else, or just the discussion around the implementation of these algorithms and data structures. So you will see more of this in future years if you choose to do future years. So here's the typical bounds that we consider when we're talking about big O. So we have a few different functions of n here that we talk about, and they're all listed on the left-hand side, starting with just c, meaning constant, meaning it's always going to be constant. If you think back to my previous video, just for a quick second for an example of this, when we were talking about stacks and singly linked lists, and whenever we needed to pull the top element off of our stack, that was a constant running time. There's no for loops involved, nothing had to shift. We just pulled it off, which was awesome. Then we have log base 2 of n, then n times log n squared, n cubed, etc. All the n to the whatevers can all be listed there, really. We have 2 to the n, and then we have n factorial. And you can see that the number of operations, like they have names like constant, logarithmic, linear, etc. And these are in order of like the best that we can come up with to like truly the worst that we can come up with. So that's what those arrows mean, by the way. I'll come back to them, but that's what those arrows mean. Like the green ones are like, yeah, that's a good algorithm. And the yellow ones are like, ooh, use caution with these algorithms. And then the red ones are like, no, these are terrible. Don't use that. Yeah. So when we're talking about like big O, we're really just looking for kind of a quick estimate of the order. And there's a really easy way to do this. We can just ask one question. What happens when we double n? What will happen to our running time? Well, we know that when we double n on binary search, the problem only gets a tiny bit faster or gets a tiny bit longer, so log n, but on a linear search, it doubles. So here we go. We have some of these reasonable spaced values. And then what happens when we double n? So log n, it's very fast, right? N just adds a little bit of time to the time. It adds c to the time, some constant value. It's not very much. For n, we end up with doubling n means doubling the time. N times log n is not that much slower than n if you think about it, because it literally is like saying, well, double n, double time, and then times some constant. Look back up to the very first line here, right? Because this basically is just like, this one here is basically like just combining these two. N squared is doubling n, you end up with 4 times the time, and n cubed means 8 times the time. Just notice that this one wasn't in there, and that's because like a function that's a constant, like a big O of 1, doesn't rely on n at all. It doesn't matter how long your list of elements is. This one does not rely on it at all. So double n doesn't affect it. So that's why there's nothing to be said here about that one. We already know that that's a pretty good running time. That's the best we can get. So ignoring the one that's constant running time, but all the others that were not red, I'll flip back one more time. You can see which ones are red here. So ignoring the first one and ignoring the last two, we have a set of these bounds that are typically called polynomial bounds, like they're polynomial time bounds. And this is important because they're computable and they depend on the input size. And those two facts are very important. Other than big O of a constant value, all the others depend on a input size, but not all the others are necessarily computable, like 2 to the n and n factorial. They basically are saying that as n grows, these become not possible to compute in a human amount of time, whereas these polynomial ones are computable in a human amount of time. Right, so here, these are the last two. These two are not computable unless you have a teeny, teeny, tiny input. If you are asked to design an algorithm ever in your life, and for some reason it ends up being n factorial, like, yeah, you just throw it out. It's not gonna work. It's not something anybody wants because it becomes infinitely impossible to deal with. Not infinitely, it becomes it's factorial operations, but like a computer can't actually deal with a growing input size of that type of algorithm. Yeah, so cool. Now we can sort of calculate running times, but like who really cares? We've seen, especially in this day and age, our computers are pretty fast. Our input sizes have never been unmanageable. Even the workplaces that we think about that probably have large data sets, they probably have some pretty powerful computers. So like who really cares? We actually do, and we actually care. I mean, obviously we do, but like we actually care at this level too. Even when we're only talking about it at this level, as first years going into our second year, as undergraduate students, without even considering past that, we actually do care because we want to make sure that we're making the right decisions based on what we're trying to do. We need to be able to make sure that when we need to pick an algorithm, when you are in your second, third, fourth year, and you're not being told exactly what to implement, you're just being told what you need to output, how are you going to pick the right algorithm, right? Well, you have to be able to know how long certain things might take and what is or isn't possible. So if we think about binary search and we ask ourselves when should we actually use it, we know some things about this. We know we have to keep a sorted list in order for binary search to work. And there are two different ways to get a sorted list. We can either keep it sorted as we're building it. So as we're reading in data, we can keep it sorted. Or if we already have a list for some reason, we can just sort it after. But remember for a second, how fast was sorting a list? If you go all the way back in your brain and think about it, how fast was it? It was slower than a linear search. Think about selection sort and insertion sort, those two together. Um, those were both n squared, right? There's two nested for loops. You needed nested for loops. They end up being on the order of n squared. Typically, the inner for loop doesn't actually run n times for those because like the problem space is dynamic and changes as the algorithm is running. However, when we're talking about big O, right, we're just talking about the order of the function, and that's going to be n squared, knowing for sure it will be definitely under n squared. So if sorting it and then doing binary search would be n squared and then a binary search, so a log n, so you end up with n squared plus log n. Why would you do that when that is going to take you for sure longer than a linear search? A linear search is just n. So all of a sudden, we have this really interesting problem where we talk about how much faster it is to do a binary search, but not if we're not given sorted data. Imagine having to sort the data first and then doing your search. Maybe that's fine on like jelly beans, but it wouldn't be fine if you were sorting the pages of a phone book. It'd be a heck of a lot easier to just do a linear search. So why even bother? Well, there are situations when it does potentially help us, and it's also worth recognizing that this is exactly why we need to know these things, because we need to know, okay, doing a sort and search makes way less sense than just straight up doing a linear search a lot of the time. So, how can you justify needing a binary search instead? Well, if your list is already sorted, then you can use a binary search and you can know that. If you know you're gonna end up doing a lot of searching, but you don't plan to do a lot of adding and removing of elements and moving around of things like that, then maybe it is worth it for you to sort it once and then search. Because if you know you're gonna have to run days and days and days of searching, it's possible that the one sort plus binary searches will take less time than constant forever linear searches. So we can now start to see how when we think about a larger problem space, these algorithms and their running times can compound on each other. And we actually have to think about that when we're trying to pick the right algorithm to implement. Um, Also, another reasonable situation is, of course, if you have a lot of time to sort it and you know you have a lot of time to sort through your code, then that might also be worth it. And we're talking about like overnight or something. So like you could set it up to sort overnight because you're sorting genome sequences or I don't know, just huge big data. Set it to sort it overnight, and then from then on, you're not getting any more input. You just need to be able to search through the genome sequences. That might actually make sense. Because otherwise doing linear searches on genome sequences could just take way longer. So we really do have to consider these different cases and what we're going to be doing in our program. We can't just pick our favorite sorting algorithm or whatever's easiest to implement and just say, well, this is going to be O of n, so that's definitely going to be faster than sorting and binary search. Because that might not be the case in like a large amount of data that you plan to do a lot of searching in. There's a lot more forethought that has to actually go into that process. So we did talk about those sorting algorithm running times, but let's actually break those down the way we did the linear search and binary search, which is not something that we've done before. We kind of just said, n for each for loop, for each outer for loop, you are running the inner for loop, n times n, we got n squared. We're gonna talk about that a little bit more now. So let's start with the ordered insert. Um, and the nice thing about doing these analyses is that they're data structure independent analyses. So it doesn't matter if you're talking about an array list, a linked list. It doesn't matter for this particular scenario. There are some scenarios where that does play a factor, but in this one, it doesn't. An ordered insert, it doesn't matter in terms of the order of the function, like the worst case scenario. If we want to do data structure independent analysis, we have to just assume we don't know the data structure. Because of course, an ordered insert on a array might be reasonably fast. We may be able to do a binary search in order to insert our value, but we can't assume that if we're doing data structure independent analysis because we could have a linked list data structure. So if we're going to go totally independent, we just have to consider, okay, but what's the worst case scenario then? It's like computer scientists all have anxiety, and this is why, because we're just constantly talking about like what's the worst scenario that could possibly happen with our algorithms. That's basically what's happening here. Okay, so how fast is this? There is only one loop in an ordered insert that goes through the array one element at a time. So this isn't the full select insertion sort. We're just talking about the ordered insert, one element being inserted into the array. A single loop, we're assuming data structure independent, so we're not assuming we can use anything other than a linear search to find the position it needs to go in. Now, it could go through all the elements and put the new piece at the end. It might insert it at the front. On average, as we know, a linear search on average goes through half the elements. So we end up with a big O of n, exactly the same as a linear search. It basically is a linear search where we move elements as we go, right? If you find the position and then move everything after, this grows. But if you do a reasonably smart ordered insert and you're shifting as you're doing your linear search, moving each of those elements as you go is just some constant amount of work, right? It's just some number of steps that you're just like picking up an element and copying it over one spot. That's just constant, and it's happening as your end loop is running. So it doesn't really affect the running time. We can still just say that the ordered insert is big O of n. Now, when we look at our insertion sort here, or yeah, our insertion sort, here's basically the code. And we're basically saying for every element of our array, do an ordered insert into the sorted portion of the array, right? This should be like old news for us at this point. So this is like the basic pseudocode for an insertion sort. It just has an extra loop that will run n times from 1 to n. We don't have to sort the first element. We assume the first element is sorted. So it's kind of like technically, like, it'll always run n minus 1 time if we wanna be, like, really pedantic about it. And then inside that loop, so for every n minus 1 times that it runs for each of those elements, it will do an ordered insert, and we know that the ordered insert is gonna be big O of n because we just said that. Um, Actually, what it does is the first time it'll do 1 step, the next time it'll do 2 steps, then 3, then 4, right? Because the first time that our ordered insert runs, there's only 1 element in the sorted portion. The next time it runs, there's 2 elements in the sorted portion. The next time there's 3 elements in the sorted portion, and so on and so forth until the very last element needs to get sorted, pardon me, and there's like n minus 1 elements in the sorted portion. So, that's actually what it's doing is more of like this like summation of those steps, 1 plus 2 plus 3 plus 4. And if you've ever done like a summation of n, there's a formula for that. And we actually do know that on average, this is about n over 2. And just as we saw previously, n over 2, we're going to knock that 0.5 off. And this just becomes an order of n function as well. So now this outer for loop runs n times, and the inner for loop is also running n times. So for each outer n, we run an inner n. That's n times n for each one, right? We can think about it like for each row, for each column, it depends how you want to say it. For each step, we have an inner ordered insert that runs up to n times. So that's n times n, that's n squared. So insertion sort is an O of n squared algorithm. Let's also look at selection sort before we finish off this video, and then we will look at the other more advanced sorts after. So let's analyze the selection algorithm now. So here we can have, this is approximately what our selection sort looks like. We have our for loop that basically runs most of the length of the array. Everything but the last element ends up getting run. We have a little bit of work that like sets up the cur min value and like an int cur min or whatever, like just some very basic statements that set up getting ready to run that inner loop. The inner loop goes and does it's like a very small amount of work if you think about it. All it does is just say, if this is a small, update the minimum value, and that just runs all the way through the whole list, well, the whole unsorted list, we should say. And then after that's done, the swap happens, right? There's a small bit of work to just do the swap. Each of the things that are a small bit of work are basically constant amounts of work. The pieces that we care about for analyzing the order of our function are the parts that actually rely on n, to decide how many times things are going to happen. So our 2 loops are what we care about here. So once again, we have 2 nested loops, both of which at a dot length minus 2 and a dot length minus 1. So technically, there's like an extra minus 3 or whatever on this. But when we think about it again, we're going to pull away those constants. Both of these nested loops are going to be O of n. Again, the inner one is only going through the unsorted elements each time, which means technically it's n over 2. But on average, we're still just calling that O of n because we're ignoring the constants. So again, this is n steps, n times. This grows at the same rate of insertion sort. This is n squared. So all of our simple is spelled weird there. All of our simple sorting algorithms, insertion sort, selection sort, we didn't actually cover bubble sort, but that's another one. These are all O of n squared algorithms. Now this means that although some are faster than others, depending on different situations, like if the data is almost already sorted, if the data is in reverse order instead of in the correct order, if there's a, if I think those are the 2 main scenarios, is like if the data is already sorted, um, some of these are considerably worse than others, or if the data is in reverse order, considerably worse than others. But basically, theoretically, they're all equally slow. They're all n squared algorithms that are pretty slow, that effectively, when the lists get very long, all these sorting algorithms just become so silly to use or almost impossible to use based on their running time, right? Think about that. If we have billions of elements, what's billions times billions? That just becomes impossible. Like, that's just crazy talk, especially when there's other options out there. So there's been a lot of work that has gone into improving um, sorting, because sorting is really important when it comes to having lots of data, right? So we need to improve on these simple sorts. And in order to improve on these simple sorts, we have to find a way to get rid of this nested loop situation, right? The nested loops, that n loop on the outside and that n over 2 loop on the inside, this is what's causing us to have an n squared algorithm. So that's a problem. We can't keep just using n squared algorithms to solve our sorting problems, or we'll never be able to do large data sets. So rather than doing these nested loop situations, we do something called divide and conquer. So we have another category of sorting algorithms that are called divide and conquer. It's similar to binary search, one of them, right? Merge sort, where we're dividing the problem space. So we see divide and conquer work when we have binary search, and it can be faster than a linear search. So by understanding that basic concept, and by understanding that it's possible to take a loop and find a way to turn it into something that is no longer a loop of all n elements, or take two loops and somehow no longer have those two loops be n squared, we can find ways to solve really, really interesting problems. And this is how we get merge sort. So in my next video, I'm going to go through the analysis of merge sort and quick sort and talk a little bit more about them as sort of an interesting way to end off the course. Some of the analysis is important in terms of what is evaluative in this course. It's important that you actually are able to compare and contrast these algorithms. Um, but you don't have to get really deep into any of the math or anything like that. But just, having a basic understanding of how we're getting these big O, these order of functions, is really important, both for this class and sort of foundationally if you choose to continue in computer science. So yeah, so meet me over in the next video where we will finish off with merge and quicksort analysis.